First, we're going to see how leftover locals can be used in a proof of concept attack on an LLM. In this terminal, we have llama.cpp, and we're going to launch that in just one sec. But in another terminal, we have the listener. And what we're going to do is we're just going to start the listener, and it's just going to hang out there. Let's switch back over to llama.cpp. All right, so we're going to start the interactive LLM session. So that's starting, and we're going to give it a prompt. Maybe something like, tell me about trail of bits. Let's see what it says. So see the LLM, gives a pretty good answer. Talks about trail of bits being a security consulting firm. Kind of what we'd expect from an LLM. Let's go see what the listener was able to find. Well, we see a little bit of garbage, like we talk about in the blog post, but ultimately we see that we're able to see a lot of information that comes out of that chat session. Specifically, we can see that they're asking about trail of bits. We can see that they're based in New York City, and we can see that they work in security. Now, an attacker could just continue to listen, continue seeing the output of the LLM chat session, and it can even be tuned to get the results with higher fidelity. Next, we're going to see how leftover locals can be used to implement a covert channel on iOS devices. So this is my iPad, and first we're going to open up the Covert Listener app. What this essentially does is it dumps the local memory and allows us to inspect the values. For example, if we just dump the values, we see a histogram of all the values it's seen in local memory. We can see that we see a lot of different values, but they don't really seem to follow any specific pattern. Now, on the iPad at least, we can take two apps and we can run them side by side. So I'm going to run the Covert Writer app next to it. And what we're going to do is we're going to implement a secret key. Now this sort of serves as an anchor for the writer and the listener to kind of synchronize on. The covert listener will look for the anchor and then try to find a message after that. So we have an anchor of ZZZ, and then for the secret message, the writer is going to write trail of bits. Now the app is going to start writing both the anchor and the secret message to local memory. And now what we're going to do is go over to the listener and we're going to try to see what we can find. So we're going to dump local memory, and what we see is that there's a lot fewer values. And in fact, if you know your ASCII codes, they might look kind of familiar. Now we're going to tell the app to anchor on that prefix, ZZZ, and we're going to search again and see if we can find the secret message. And in fact, you see that we are able to find the secret message. And this just shows that the leaking local memory or leftover locals can be used to implement covert channels in iOS devices, especially when you can run apps next to each other, like on the iPad. Now we're going to show how we can see that same covert channel on an iPhone. So this is my old iPhone 12. I'm going to open up the settings just to show that that's what it is. And there you go, iPhone 12. And what we're going to do is we're just going to go to that Covert Listener app and we're going to try dumping local memory again. And just like before, we see a lot of different values don't really seem to follow a pattern. But in the iPhone, you can't run the two apps side by side. So instead what we're going to do is we're going to provide that anchor, just like how we saw last time. And we're going to go into the writer, again, provide the anchor of ZZZ, give it a secret message, hello from covert channel, and we're going to write it, and now we're going to swap in and out of the apps. And what you can see is that when we swap into the listener from the writer, we are able to see that secret message. Well, we're able to see it most of the time, but you can see that it's writing, and now we swap in, and we're able to see it again. And so now you can see that even though we can't run the apps side by side like on the iPad, we can still see the effects of the leaking memory when we switch in and out of apps. Continuing our tour of Apple GPUs, now we're going to see leftover locals on a Mac OS device, and specifically this is my M2 Mac Air, as you can see here. We're going to use those same apps, just the Covert Listener and the Covert Writer. We're going to dump the local memory. We're going to see that we see lots of values again, and we're going to give it that anchor so that the covert channel can kind of synchronize on that anchor. So as we've seen, we're just going to use ZZZ. And we are going to start writing. We're going to give it a secret message. Hello from the covert channel. We're going to start writing that to the GPU. Then we're going to open up the other app. We're going to start looking. And This one we don't see it as with quite as high fidelity as we did on the phone and the iPad, but we think with a little bit of effort you could figure out the structure of the leaked data and still get a lot of information from this data leakage. Moving away from Apple now, we're going to look at mobile Android devices. This is an HTC One 11, and this has a Qualcomm SoC and a Qualcomm GPU. So we have similar apps on these Android devices. We have a listener and a writer. And first we're going to launch the listener. So you can see here that we can dump memory, similar to what we did in the iOS devices. So if we dump it, you can again see the histogram, and you can see that we see a lot of different values that are not zero. The app also allows you to iterate several times and dump the local memory over and over again, and we can also search for a canary value, or one of those anchors that we are using in iOS. So now let's open up the writer. Unlike in the iOS app, in this case we just write a canary value, in this case 1, 2, 3, and again we have a number of iterations so that we can just write this over and over and over again. Android devices allow you to run two apps side by side, at least some of them do. So what we're going to do is we're going to run the writer and the listener side by side like how we did in the iPad. Now what we're going to do is when we write, we're going to write multiple times in a row. In this case, we're going to choose to write that canary value 256 times. That is 256 kernels. And now in the listener, what we're going to do is we're going to launch several kernels, 16, to try to find that canary value. So let's see if the listener is able to see any of those canary values from the writer. So we're starting to write and we're starting to listen. And in this case, you see that we didn't see any instances of that canary value. But let's try again. Now you see in this case, we actually saw quite a few instances of that canary value. So in our Android devices, we see that we don't see the leakage quite as frequently as we do in the iOS devices and the Apple devices, but we still are able to see it. And this app can help test for leftover locals on Android devices. Lastly, we're going to look at the command line interface using Vulcan, and we're going to go back to that AMD GPU that we started out with. And again, this similarly uses a covert writer app and a covert listener app. So we're going to have one processor run a covert writer, and this just writes the canary value 1, 2, 3 over and over again and prints a dot every once in a while. Now we're going to move to the listener process, and we're going to dump local memory, and we're going to get a histogram of the different values that we see. And it's going to periodically dump local memory and show different histograms. And what you can see is that while we see a lot of zeros, we also see a lot of those canary values, 1, 2, 3. And in fact, the different processes can be tuned so that we see even more of those canary values. And in fact, we need to see more of them to implement that proof of concept on the LLMs that we saw earlier. And that does it for this video. Thank you for seeing all the different ways that leftover locals impacts different devices, and let us know what you think. Thanks.